So we got Sondy's bookshelf there. There she is. She's returned. Phew. Well, hey everyone. My name is Fraser Cain. I'm the publisher of Universe Today, and this is your weekly space hangout for Friday, May 16th, 2014. So, Sondy, there's like a background hiss that's coming from your microphone.
Let me try one thing.
Try a new microphone. I'm going to mute you. Okay, so this week we're going to be talking about... Man, come on, browser. It's so professional. We're going to be talking about Arecibo looking under the lunar surface, the red spot shrinking on Jupiter, update on Bicep 2 rumors using the interstellar media as a pulsar lens, neutron stars as a solution to radio bursts, a lot of astronomy this time around, Rosetta's comet has flared up, a conjunction of Phobos and Jupiter from Mars, failed Proton launch, funding for Kepler, and imaging an exoplanet for the first time. Well, not for the first time, but recently imaging another exoplanet. All right, and joining me this week, let's see how this works, we got Sondy Springmann at the Arecibo Observatory. Hey, Sondy.
Hello.
Hey, that works great. It sounds great. It looks like you're in some kind of mission control. So that's perfect.
See if we can see the. Well, we can't see the telescope today. It's hiding.
How is that even? Isn't it like a gigantic superstructure?
You can sort of see it out the window on the left, to the right of the hill, but the dome is hiding. You can just see the antenna.
All right.
We'll be talking about this antenna later.
All right, we'll take your word for it. That you're actually at Arecibo Observatory and not in some kind of cunning mock-up in a NASA studio somewhere. Brian Koberlein. Hey, Brian.
Hi.
You are a professor at Rochester Institute of Technology.
That's right.
But now you're at home.
Now I'm at home, yeah.
No classes?
Yeah. We just finished up classes this week, so I still have a final to give, but basically it's the home stretch.
But the teaching via the Weekly Space Hangout and Google Plus goes on.
Goes on.
Dr. Nicole Gugliucci.
Mine's the sun. Sorry.
What's going on? What's the news?
I don't know. There's music in my head. It's fine.
Care to share that with the rest of the class?
Did
No?
anybody get that reference? Oh, mine's the sun. What's your favorite planet? Mine's the sun. Alright. I'm going to let the commenters figure that one out.
So I'm going to give a special what's up to Roshan Bukhari, who says, hey guys, I'm waiting for the Hangout to start. Been waiting a whole week to see this live and participate. So Roshan, welcome. The week. I'm so glad we could make your week totally worth it. But the way that you can interact with us and respond is to use the Q&A app. So we're using that right now. If you go, you'll see somewhere, wherever you watch this on YouTube, there's a little link that says that Fraser has answered questions from the audience. You click that, and you'll get sort of a list of questions that have already been asked and a way for you to throw stuff in there. So, right. So let's get on with the first story. What do I want to talk about first? Okay, you know what, Brian? I want you to talk about the Bicep 2 results and how there might be a problem. So I guess a bit of a background, right? People announced that we had saw evidence of inflation in the afterglow of the Big Bang via the polarity. This is it, concrete evidence for inflation, except maybe not.
Right. What they were looking at was polarization within the cosmic microwave background, specifically something known as B-mode polarization. And Bicep 2 announced that they had detected this and that had detected it at a strong enough level that it indicated early cosmic inflation. Of course, it hasn't been peer-reviewed yet, so it's still going through the peer review process. And one of the big challenges is something called foreground effects. Basically, the cosmic microwave background is the most distant light that we can see. So everything else, galaxies, interstellar gas, everything, is in front of that. And so you have to take that into account in order to make sure that what you're seeing is actually the cosmic microwave background. A while back, there had been a paper that came out that looked at one effect that they may not have taken into account, which was due to dust spiraling along magnetic fields, what are called radio loops, creating polarized microwaves that could look like this B-mode polarization.
How far away would this dust be?
It would be in our galaxy.
Right.
So it's in, basically our galaxy had these, intergalactic magnetic fields. Dust can get trapped in it, and as it spirals along the magnetic field loops, it can create, microwave radiation. And it's polarized because the grains are not symmetrical. So it has an orientation along the long side of the grain. So there was a question as to whether or not this had been taken into account. And when you go through the details, BICEP2 took some of this into account, but they did it in kind of an unusual way. Because what they wanted was data from Planck, which has been specifically looking at some of the foreground effects of the magnetic field. That hasn't been published yet. So what they did was they took the results as presented in a conference presentation from a PDF slide. And they basically took the PDF slide and then reversed the data from the PDF. So basically you have this map, and from the map you can get what the foreground effects are from this dust, and then you can subtract that out. And depending on who you talk to, some will say, well, this is a huge problem, because there's a question about whether or not it's actually the polarization or an average of the polarization. If it's an average of the polarization, it's not very useful, because it doesn't take into account the foreground effects. If it's the polarization, then it would be useful, but it's still not the raw data. So it's basically convert it to PDF and then reverse back the data to get back to it. So this has caused a big brouhaha, and some are saying, well, this is very likely going to invalidate BICEP2, and others are saying that no, it's not going to invalidate BICEP2. My own take on it is, as public as this comes out, this is how science is done. This is part of the peer review process, except that now it's everywhere instead of just being in the ivory tower. I don't think this data alone is enough to invalidate the BICEP2 results, because it's not the only thing that they've taken into account in terms of the foreground. There's a lot of effects that they've taken into account, and this PDF file is just one of them. So it could affect the results, but I don't think it's going to negate the results.
So you think they've still found evidence of inflation in the cosmic microwave background radiation?
I think they very well could have. I mean, you have to be a little bit careful, and because it's such a big claim, we want to see multiple results from multiple sources. So if we come through with Planck, and Planck has a similar result, then we'll be more sure. I mean, part of the reason why this is so public is that they came out with the result first. So if they're valid, they kind of have claim on the Nobel Prize. and so, I mean, this is big political stuff as well as being big science stuff. Planck, if BICEP2 is wrong, then Planck will likely get the first official result of inflation. So there's a lot of competition there, which is not a bad thing. But from what I've seen so far, I don't think BICEP2 is invalidated simply by this. If other things come out, then maybe.
Okay, that's great. I thought you're going to be a lot harsher on them, but actually that sounds still pretty hopeful. And
yeah, I mean, taking something from a PDF is one of those kind of, I want to say it's an act of desperation, but it's not an act of bad science per se. Sometimes to get a scoop on data, you get them from kind of roundabout means, and it's still valid data. And again, it's not the only thing that they've had. It's not like this is the only way they've gotten the foreground effects. There's a lot of things that they're putting in there.
Right.
So,
but to actually sort of confirm this, you'd want some way to really detect the motion of these dust lanes within the Milky Way using some other way and see if they match up with the lines that you're seeing in
Planck has done an initial survey of that. Planck has an initial map of the magnetic field lines that it's gotten from the oralization of the polarization there. So this is all coming up all at once. Basically you have all these teams kind of coming in, and so it's going to be interesting.
As you say, it's big stakes. I mean, this is full-on Nobel Prize.
Stakes.
Yeah.
Yeah, I mean, this is Nobel Prize level work.
Yeah. I mean, going all the way back to the sort of theory of the Nobel Prize. I mean, of the inflation. Like, is everybody gonna was it Guth who originally?
Yeah, you're gonna get
Yeah, who came up
and
with.
I'm trying to think of the other guy's name.
Yeah, so I mean, would he
One
get
that's
his Nobel
familiar with,
Prize,
but
and then all the discoverers would be able to get the experimentalists, etc. So yeah, this is a big deal. All right, let's move on. Sondy, why don't you talk about your work attempting to peer beneath the moon? Well, not your work, but
This is actually not my work, but it's a colleague, Lynn Carter, and she's been doing radar studies of the moon. So why are we still studying the moon's surface? It's, we sent the Apollo missions there, we've had spacecraft orbiting around it. The cool thing about radar is, among its other great party tricks, is that radar can penetrate the surface of what it's looking at the scale of the wavelength. So in other words, if you have a radar wave that's about 70 centimeters long, so less than a meter, it can actually penetrate up to 70 centimeters-ish into the surface of the moon. And that's really cool because the moon is covered in dust. There have been impacts on the moon for as long as there have been things to hit it. And those impacts can actually generate dust. There, it's called impact gardening, which is probably what I'll be doing in Tucson. So it actually breaks up rocks on the surface and creates this dusty layer, this regolith. And so because of the dust, because of this soil layer on the moon, you actually can't see below it, and you can't see the history of the moon. So radar actually will penetrate the surface of the moon and let you see what's going on. And so they've been studying, Lynn Carter and her colleagues, they've been studying sort of below the surface of the moon, not sort of, below the surface of the moon. They've been looking at impact craters, and this really lets you look at some of the older geology on the moon, and you can see how the lunar rock melted and get a better size of the craters and really just get an idea of the complex history of the moon. And you can also do this on Mars as well. You can see below the surface, and you can see old lava flows that you can't do otherwise.
so what are some of the kinds of features that they've turned up?
They've been looking at a lot of craters as well as a lot of volcanoes. So they can see a lot of lava flows that happen when these craters form, these impact melts. So that's kind of cool.
I know that like back in the Apollo era, they weren't even sure how deep that lunar regolith went. Like they weren't sure if they were going to, sink these landers right into the lunar regolith, or were they going to be able to sit on top? So I mean,
Exactly.
does that give them a better sense of like how deep this stuff is?
I mean, so it looks like these observations were actually be able to go more than just 70 centimeters. They're actually able to go see about 10 to 15 meters below the lunar surface. So that's kind of cool. And no one else is really doing this work looking at the surface of the moon. So the fact that you can do it with ground-based tools is pretty cool.
That is awesome.
I will add that while Arecibo did the zapping, the Green Bank telescope in West Virginia, one of my favorite telescopes, did the receiving of the reflected zaps.
Well,
the radar.
my favorite telescope is the one sending out the I think they send out continuous waves, and it's actually they're using the radar that's usually used for atmospheric work. So this is moon bounce, pure and simple, for all of you ham radio nerds out there in Hangout land. And so you send signal from Arecibo, it bounces off the moon and is collected by Green Bank. And the reason we do that is it takes about 8 seconds to go from transmit to receive at Arecibo Observatory, and the moon is what, a second away, a couple seconds away. Anyway, it's too close to zap and receive at Arecibo, so you need to call up a friend.
Okay, so now we don't have any people who worked on the story, so I'll just give sort of the synopsis, and if anyone wants to jump in, they can, which is the story about the Russian Proton launch failure. So this was yesterday, and I remember a bunch of people tweeting that this Proton successfully launched, and there was some cool video of it, and then about 540 seconds, it detonated and destroyed the satellite on board, and it all crashed back into the atmosphere. And so that was yesterday. They don't know why yet, and that's all we got. So it was the third stage. So I don't know if you know the Proton rocket. Third stage is the BRIES-M, and that is what experienced a emergency engine shutdown after the rocket veered off in a direction it was not supposed to. And so we've had 6 of those failures in the last 3 to 4 years on that rocket platform. So I think there might not be a lot more of these. So that's all the information we have right now. Let's move on to Nicole. It is sad. I mean, protons have been launching for decades and decades. So go ahead. Why don't you talk about the Rosetta's comet? And I want you to say the comet.
Yeah, let's try this.
Haven't you heard Emily Lakdawalla's version of this? I'll let you try and say it, and then I'll give you hers.
No, I don't think I have.
Okay.
So this is the comet that the Rosetta spacecraft is heading towards. This is comet 67P Churyumov-Gerasimenko. What does Emily say?
She calls it Churi-Zuri, I think.
Churi-Zuri. All right,
Yeah.
Churi-Zuri. Comet Churi-Zuri is being visited by the Rosetta spacecraft. This will be the first spacecraft to actually fly alongside the comet, orbit inside the coma, or the tenuous atmosphere of the comet, and actually send out a little lander to the surface of the comet. So I'm really looking forward to this. This is really cool. And for the first time since Rosetta's been chasing this comet, it actually looks like a comet, in that comets are pretty dull and boring when they're out in the outer solar system. When they get closer and closer to the sun, they will start to sublimate. This is the oh, I'm trying to find that GIF.
I got it. I got you covered.
You have the GIF? Not the one that moves. But
Oh,
yeah,
not the
there
one
you
that
go.
moves.
There's the comet. That's the comet. It's starting to sublimate, so the ice is on it. It's got water ice, carbon dioxide ice, ammonia ice. These are typical constituents of a comet are turning into gas as it gets closer and closer to the sun and starting to create the coma and the tail. So it's starting to become active. The rendezvous... When is the rendezvous scheduled? I should have this... Oh, here we go. Rendezvous is scheduled for soon. When does the rendezvous start? Does anyone know?
The
Is
actual
it near the end of this year?
Yeah, it's at the end of the year. November,
November? Okay.
I think. Yeah.
Okay. It's near the end of this
Let me
year,
dig it up.
and then it's going to spend about a year. It's scheduled to spend about a year studying the comet before it ends its mission at the end of 2015. So I was because I like images that move.
So you have a GIF. Oh.
Well, I can show it in my web browser. So there you go. It's circled in red, and it's moving along, moving along. Ah, look at the tail! It finally gets warm enough, crosses the frost line. And it looks like there's actually a globular cluster in that picture as well, which is just kind of a freebie, which is kind of nice. That's my guess as to what that is anyway.
So the orbital insertion is in May. And then it's going to land. Oh, that's right. And then it's going to try and land later on this year.
Boop. Yes. And I've decided it's going to make a boop sound when it lands, as opposed to Deep Impact, which went, which didn't quite land on a comet, but the Deep Impact probe smashed a thing into a comet so that we could see what came out. That was really fun to watch live on NASA TV when that happened. I see Sondy's doing the boom over there.
So yeah, so the Philae lander is going to touch down. It's going to be attached in November 2014.
Okay.
So it's made its approach, and now it's going to actually attach the lander. It's going to attach to the comet. It's going to harpoon the comet in November, and then it's going to drop the lander down to the surface. So
yeah, so this is going to help them out figure out what the comet's doing. It's going to get a little dicey as they get closer because it's going to actually go into the coma where all this material is in off the comet. I'm all full of sounds today. So this is these
sound effects, space sound effects from Nicole.
Sound effects! There are no sound effects in space. So they're going to actually, because as they say, comets are like cats. They're just about as predictable. So they do have to watch it pretty closely to make sure it's still on track, so they can rendezvous.
Speaking of cats, Sondy's been cut up by one.
I will show you a photo of her if you'd like to see.
Well, let's see your
Real
horrible
cute.
wound, and then.
If you're not following observatory cats on Twitter, you should.
So this is Oyster. I don't know if you guys can see her here. She's perched above the dish. This is maybe 300 feet above the surface of the dish. Can you all see that?
Yeah. Wow.
She's a gorgeous cat. She's kind of this tabby, and she's got she's a white tuxie. Anyway, she's pretty, but we think she may be she's a girl cat. And for girl cats, you need to You need to take care of them. So I tried to catch her today, and there was blood and gore. And anyway,
Oh,
we'll try again. So we'll
don't
try
you
a
have
bigger
some
box.
kind of like tongs or like a hook or like some kind of machine that you can use to pick them up?
I was watching this video yesterday on how to properly put your cat in a box, and it was like that works great if you don't have a stray. Anyway, this was my community service for the week, and we'll try again. We have 7 weeks before I leave Arecibo, so we've got to fix all the cats. It's like, like Pokemon, got to catch them all.
Right, and bring them with you and find them homes.
If anyone in San Francisco, Dallas, Los Angeles, or Boston would like a cat, let me know.
Okay, Brian, using the interstellar media as a pulsar lens.
Yeah, this is kind of an interesting thing. You've got basically a pulsar is a neutron star that's rotating, and because neutron stars have strong magnetic fields, they create beams of energy, radio waves, sometimes invisible, that radiate out from the poles. And there was a recent paper that looked at how radio waves coming off of a pulsar interacted with the surrounding interstellar media. So the radio waves are radiating off the poles of the neutron star as it's rotating, and it's interacting with the interstellar media. And what they did was, because they know the timing of the pulsar and because they know the timing of the radio waves, they could actually use the distortions of the radio waves by the interstellar media as a way to increase the resolution of what they could observe. So it's similar to the way we would use multiple telescopes and develop an interferometer so that you can make kind of a virtual large telescope. They did a similar thing with what's called speckle, the reflection of light that kind of flickers in and out with the interstellar media. And so they analyzed that and were able to get down a resolution on the order of pico arc seconds. So I think they got down to 50 trillionths of an arc second, and an arc second is a 3600th of a degree. So basically, this is kind of a resolution of 10 kilometers from 2,000 light years away.
Just another example of us using big spinning rocks and even mysterious dark matter and things like that as just another telescope.
Right.
You know?
What's interesting about what they found was that with this resolution, they could show that the radio waves are actually emanating from a region much closer to the neutron star than we thought. So basically, you kind of figure that the radio waves are in this outer region, but actually they're pretty close to the surface, which is interesting. What exactly that means, I'm not entirely sure. But to get that kind of resolution means that we can better understand how these pulsars actually generate the beams of energy that they have.
That's really cool. Nicole, did you work on this? No. No? Okay.
I got nothing.
It was like a radio.
I have a
wave.
non-detection of a magnetar somewhere in my publication history, in a telegram. That's about it.
I looked for a magnetar and I didn't find it. Was that your paper?
No.
It was astronomer's telegram. Yeah.
Are you a member of the Arecibo Non-Detection Society?
No, this was a VLBA project or VLA. I can't remember which one we used. We
What
were
is a
summer
non-detection
students.
society? Is this where I went looking for a thing and I didn't find it? Please don't also go looking for it.
Or, this didn't happen. Well, a lot of the time it's also, we have the Arecibo Non-Transmit Society as well, and it has proceedings of the Arecibo Non-Transmit Society, pants and ants. Anyway, so either things don't work, or things don't work, or something blew up, or whatever.
I'm definitely part of that society for the Green Bank Telescope, if there is one, so I'm sure it's broken things there.
Journal of Null Results.
Yeah, right. Null result.
I have a null result in my publication history.
You don't see a lot of those null result papers.
That's why it was a telegram. It wasn't a publication. It was just don't bother unless you wanted better than our sensitivity.
You could do data mining, then it would just be the Journal of Noise.
Adam Synergy knows.
Noise.
Hi everyone, I've managed to drag myself away from watching the awesome live footage of the ISS flying over California. Have you guys watched the live camera on the
Yes,
International
and I
Space
would like
Station
to know what music people are playing while they're watching it.
while they're watching it?
Yes, I feel like there's got to be like a playlist of awesome stuff that goes along with that camera feed, and I haven't gotten any responses yet because I just blogged about it on CosmoQuest. So let us know.
Let's figure that out. We should totally. We'll build a like what? We'll do one on Google Music, and we'll do one on like Spotify, and then
A
there'll be like
playlist.
this playlist.
Yeah.
We'll get people to suggest the playlist songs that you should listen to while you're watching this feed.
I figured Hulse the Planets was
Yeah.
appropriate,
Yeah.
but anything by Daft Punk would work as well.
Yeah. Yeah. Flight of the Valkyries or something. I'm not sure. All right. Well, let's move on. Sondy, apparently Jupiter's Great Red Spot is shrinking. Now, this turned out to be no surprise to you.
I guess I'd been reading this for a while, but people have been looking at Jupiter's red spot for 300-something years, 400-something years since people have been pointing telescopes up there. And it turns out it's been getting smaller and smaller. Voyager flew by in the 70s, and we've been looking at it with Hubble, and it shrunk from about 21,000 kilometers, that's 13,000 miles for those of you imperial people. And now it's smallest yet at 16,000 kilometers and just under 10,000 miles. So we've been seeing this spot get smaller, and no one really is sure why it's getting smaller. Maybe it's got some eddies that are sort of messing with its size. But the cool thing for all of you who remember back to introductory mechanics, physics, is that as the spot shrinks, it spins faster. So just like that ice skater who brings in their arms and they start spinning faster while spinning, it's the same thing with Jupiter's red spot. So I think that's pretty cool that angular momentum conservation still works even with fluids, and that this thing is, it's as the Universe Today article says, it's got a shrinking waistline, and it's shrinking by about 1,000 kilometers per year. So that's pretty serious.
Yeah.
So will we lose it in our lifetime?
So it's 10,000. What is it? 21. It's 16,000 kilometers now, and if it's it would be shrinking. So if it's shrinking by 1,000 kilometers per year, so that's another 16 years. It could disappear.
Mm-hmm.
Who knows? But who knows?
Could it hit some
really
certain size and then be able to get torn apart by some of the other weather systems and other storms and stuff? I know you're not
I am not a weather
planetary
person. We'll
meteorologist.
have to get someone who actually does fluids and things that aren't solid. Low energy. We'll have to get a low energy astrophysicist on the show next week to answer that.
All right then.
Did you see me try and do it? It wasn't working. I have too much friction in my chair.
You were trying to
I don't have
spin?
enough space here.
You want to? Oh, you have too much friction. Okay.
I was trying to like demonstrate with like the arms pulling in, but then I slowed down. It's friction. But you can grease up a chair and make it like almost frictionless, because I've done this in physics class before, and you can show. It's pretty fun.
I wonder if anyone's ever done the math on what is the biggest possible storm that could be on Jupiter and how long it could last.
Well, there's that really big one on the North Pole of Saturn, that hexagon that has been there since the
because
Voyager
otherwise
era.
differential rotation would kind of mush it up, wouldn't it?
Mm-hmm.
Something that's not at the pole.
There you go.
Closer to the equator, you'd have more problems.
So
I
there you
want
go.
to
That's
learn
my question.
atmospheric stuff. Good thing I'm going back to grad school.
Ask them if they'll teach you some atmospheric stuff.
That is the goal. Though this fall it'll be plate tectonics and cosmochemistry.
Wow.
What will you eventually get a PhD in then?
Lunar and planetary science. So in 5 years it'll be Dr. Crazy Cat Lady to you.
There you go.
It'll
Join
be
the Crazy Cat
three.
Club.
It'll be
Woo!
3 PhDs here. Okay, Nicole. You put this in as boop, Phobos and Jupiter conjunction from Mars.
I just look at this series of images and I think, boop! This is actually an older image, but there's a more recent story that I can tie into it as well. This is a series of frames of Phobos and Jupiter from the Martian sky, and so you have them a little conjunction, and when I see this I go, boop! But this was featured on the ESA's website, European Space Agency, showing that conjunction, and I think part of the reason for showing that, where's the other one? I like things that move. There was a occultation of Saturn by our moon, as seen from our planet, seen from Australia and New Zealand. So we've got some. I know you guys have on Universe Today have some pictures from Ian Musgrave and Peter Lake. So our buddies out there. Peter Lake, in fact, did a hangout. So I really, really love this picture from Peter Lake. This is one that we shared out earlier. So there's Saturn getting ever closer or heading behind the moon. And then, of course, Ian Musgrave put together a nice little GIF of Saturn.
Oh, look at that.
Hiding behind the moon. So those lucky Southern Hemisphere observers get to see cool things again. So thank you to those guys for sharing the images. So I thought that was cool that ESA brought back the Phobos and Jupiter conjunction around the same time as this Saturn moon.
It's always amazing to me. There's actually like a couple of these conjunctions a year. Like sometimes it's Jupiter, sometimes it's Saturn, but it all just depends on where you are on the Earth, and it really shows you the trigonometry of this situation, that you can be a few thousand kilometers away from somebody and see Saturn completely pass underneath the moon, but if you get to the right spot, then you'll see Saturn go right behind the moon.
I remember when we were doing the Venus transit back in 2012, we had different observers at different locations, and they were seeing the touch points at different times. And so, because we have this global network of astronomers just looking through their telescopes all over the planet, you can start to get a sense of the geometry, and that's really fun.
Yeah, and that was the ways. Oh, go ahead.
From the asteroid occultation perspective, if you have an asteroid and you watch a star go behind it, and you have a bunch of people at different latitudes on the Earth watching the star go behind it, you can get chords of the asteroid. So someone up in the north might see it go like that, someone might see it go like that, and you can actually get estimates of the size of the asteroid or even the gross shape, or even if it has a moon from these occultations. So it might sound, just sort of silly, or some of the astrological people may go wild, but you can actually do really cool science with occultations. And the best part is you don't need a ridiculous telescope in order to do it.
Mm-hmm.
Yeah,
so
I mean, some
amateurs can contribute.
Amateurs are, not occultations, but amateurs are seeing like microtransits, gravitational microlensing, and they're discovering planets around other stars using this same process, where they're watching how the foreground star dims as something is passing in front of it, and it's amazing. So if you have any interest in participating in astronomy and you have a setup, definitely get involved in some of these occultations. Oh no, Brian Koberlein, I was about to throw a story your way, so why don't we just go with something else here?
I had to refresh because it was freezing on me, so maybe he's done the same.
Yeah, I've had some problems. Okay, so let's talk briefly about Kepler then. Now, have you been following this story at all, Nicole?
Brian's back. Yay.
Brian's back? Okay.
I'm bad. I'm of the exoplanet.
Exoplanets. If they're not listening to radio, I don't care.
It's not true. I like
radar love.
So Kepler sounds like an alien or something. So the Kepler mission thought
got
to
the
be
go-ahead, is what I know.
Yeah. So what happened was Kepler failed. Why did they fail? What were they? Didn't send enough on their spacecraft. Oh, right.
They bought bad reaction wheels.
Didn't have enough reaction wheels. Always send more reaction wheels. I really wish mission planners...
Don't necessarily send more reaction wheels, just don't buy them from that vendor. That vendor has provided reaction wheels to spacecraft, and they have failed. They failed on an Indian spacecraft going to the moon. They failed at a couple other places. So we are now sourcing reaction wheels from other people that do not have such a bad history.
Oh, I didn't know.
Figure out who supplied reaction wheels to Kepler. Don't buy them for your spacecraft, kids.
Oh, interesting.
Anyway.
Okay.
Yeah,
sorry, my rant is over.
For a government mission, you don't have a choice in a bidding situation where you're going to get your things from.
So anyway, they've figured out how to get it to work partly, and they've got a new version of the mission. So K2 is going to be starting up, and that's going to be funded through 2016. And so they're going to keep being able to look for planets all the way through 2016, which is key, because it's those long observations over multiple years when you really build up that evidence for the Earth-sized exoplanets, and so this is really going to be great to keep this mission going. And
it's actually a whole new mission. They're not looking in the same.
They're not looking in the same spots. Oh, okay.
Yeah, because they have to use the solar pressure as kind of the third balance point. And then they have the 2 remaining gyroscopes that they can balance it from. So they do it in part of an orbit and then switch and then redo it and then switch and then redo it. So they're actually looking at, I think, 4 different spots
That's clever.
over
That's
its
really
orbit.
clever.
Just to
But
step back oh, go ahead.
I was just going to point out that the data from the original mission is still being analyzed. There will still be exoplanet discoveries from when they had all the reaction wheels working. So that there's really not an end to that original data set yet.
Those Earth-like planets in the habitable zone are in that data somewhere. They just have to tease it out.
There are 2 cool things about Kepler from my perspective. One is that the PI, Bill Barucki, he doesn't have a PhD, he has a master's, so he had to work extra hard to get this mission going. And the other thing was that for years all the haters were hating, and they were saying there's no way that you can put a spacecraft at this size with this sensitivity and that it's going to discover exoplanets. No one thought that this occultation technique would actually work, that looking at the light curves as planets pass in front of and behind stars would actually do anything for discovering them, and that they were able to actually demonstrate that this works, and not only were they able to demonstrate that it works, but that it was wildly successful. So go team no PhD and go light curves, because light curves are the best.
That is awesome. Okay, Brian Koberlein, supermassive neutron stars is a solution to fast radio bursts.
Yeah, this is an interesting article that came out. There's these things called fast radio bursts, and what's interesting about them is they are, assuming that they're distant, they are very bright. They last for something on the order of milliseconds, and they only happen once. So they're kind of like gamma ray bursts, which are these really bright things from, supernova explosions and things, but they don't have any corresponding X-rays or gamma rays or anything like that. They're just a burst of radio waves, which is really weird. And the first one was found in 2001, and then recently they found several more. But we're not entirely sure what they are. I mean, they're these short-level bursts, and we're not sure what the cause is. So there's this paper put out that proposed that they could be due to neutron stars that would normally collapse into a black hole because they're more massive than an upper limit. Basically, if you have a supernova that's the core is collapsing to a neutron star, there's a limit called the TOV limit. It's kind of like the Chandrasekhar limit, that basically the neutrons can push against the gravity up to a point. And if you get more than about 3 solar masses, gravity is just too strong. It collapses in on itself into a black hole. So what they proposed was, if you have a fast rotating black hole, so if you have a fast rotating star that then goes supernova, the core could be this fast rotating neutron star. It could have more mass than the limit because it's spinning so fast that it's basically kind of flung out a little bit because of the centrifugal force. So what would happen is, you would have the supernova, it would form this neutron star that's above the limit, and then it would be spinning. And because it's spinning, and because it has a magnetic field, it radiates energy and gradually slows down. So it would be above the limit and then gradually slow down and would reach a point where it collapses into a black hole.
Wow.
So what's interesting about this is the supernovas long happen to go. So there's no X-rays and gamma rays. There's just a neutron star that's putting out radio waves. But when it collapses, a black hole that has no charge can't have a magnetic field. So basically what happens is, when the neutron star collapses into a black hole, it pinches off the magnetic fields, and the magnetic fields basically snap into a new position, and they would create this burst of electromagnetic waves. So you would get this very bright, very short electromagnetic burst and nothing else, because everything else just collapsed into a black hole. So it's a really ingenious way of describing how you could have these fast radio bursts. We don't have enough data to confirm that this is the case, but it's a really interesting idea. I personally find it kind of compelling. So
I wonder how long that neutron star had been rotating for, because I know, like, the difference between pulsars and neutron stars is just a few million years for the pulsar to radiate a lot of its energy.
Pulsars are neutron stars.
Yeah, pulsars
well, they are, right? So the point being that a pulsar becomes a more regular neutron star because it's radiating away all that energy as it's spinning, as it's got those magnetic field lines, and they're all twisted, and it's firing out beams of energy. It eventually slows down to the point that it just becomes a regular neutron star. So, but I wonder how
the neutron stars are just because the pulsar beams aren't pointing in our direction.
But isn't it losing its speed as it can
turn off?
They do.
They
can turn off. Yes.
Yeah. And so the same kind of situation, but instead of it turning off its beams, it's just disappearing into a black hole. And the only thing that was keeping it going was that it was rotating fast enough to keep itself inflated. That was the only force that was keeping it out. That's amazing. Just amazing. I'm totally stoked on that one. Richard Strassel asks, this is a question for Sondy, I guess. So will the radar be able to detect the Nazi base, alien spacecraft, giant monster hidden on the moon?
Wait, one more time?
So will the radar imagery be able to detect the Nazi base, alien spacecraft, giant monster hidden on the moon? That would also go for the pyramids on the moon as well, but...
Well, I thought the hidden Nazi base was on the far side of the moon.
On the far side, yeah.
Right, all that stuff's on the far side, and so that's not visible.
Yeah, so sorry,
from the near
that's
side.
beyond scope of what Planetary
Love
radar
that movie.
can do.
Thank you for that.
Oh, we can see the telescope. The people from Lincoln Lab are here installing a super secret radar receiver thing. Let me see.
I love when the super secret people join in. We had that at Haystack too. Like, we're doing secret things. Hey!
We had that at RIT, but...
Look at it moving. That's really cool. Elad Avron asks, can anyone tell me about the star that was discovered lately that was a twin of our sun and came from the same star nursery? Did anyone work on that story?
Well, I didn't actually follow up on that. I'm really excited about it, and I didn't have a chance to read it.
Yeah, same.
Speaking of bistatic radar, a couple of weeks ago we had a problem where one of our receivers here warmed up. And usually we keep our receivers in like 20 Kelvin, 30 Kelvin. We've got a bunch of liquid helium that run most of the weight up in the receiver dome is full of receivers and chilling equipment. And so this was a problem because we had this asteroid we needed to zap, and it was the most exciting asteroid of the year. It was like 1.2 kilometers across, and this was the best thing we were going to get. Last year, I think our best one was 3.2 kilometers. So we're like, we really need to get this one. It might be potentially hazardous. It might be a human exploration target. So my boss, Ellen, she called up the director at Green Bank, Karen O'Neill, and she said, hey, Karen, can we coordinate with Green Bank? This was the night before they were making phone calls, and Karen said, sure. So we got time in the Green Bank telescope at the very last minute and managed to get things working. I don't know really how that worked. I was about to go off to do NASA stuff somewhere. It was like furiously typing away on the computer as all this was going down. It was really cool that it worked out, and we got really great images from the Green Bank of this wacky little asteroid. So I think I may have some of them.
And is it a good target for human exploration?
It's spherical. It looks like... Oh, come on, where are you?
Are we doomed?
No, not today.
Okay.
Worry more about climate change.
Yeah.
Yeah, that we should be worried about.
Right.
Here we go. All right, let's look at this. Let's do another screen share. Anyway, this one was super cute. See it?
Ooh.
So these are 5 images received with Green Bank. And the cool thing about this is actually we didn't quite have the ephemeris of this asteroid, right? So it's actually sort of drifting in time as we zap it, and that's in delay. So it's moving where we think it is isn't quite right. So it's actually moving a little faster towards us than we thought it was. And so you can see little speckles. So those are boulders. It may have some craters on it, but for the most part, it's just a spherical asteroid about 1.2 kilometers across. And it's actually likely not a solid monolith. It's much more likely to be a big kind of rock pile, sort of a rubble pile, a bunch of gravel. Rubble pile, gravitational aggregate, I think is the polite term that we used in mixed company.
I got a question. So poor Rashan Bukhari has been trying to join us and watch the show and hasn't been able to, but he was able to get in a question, which is it possible to have a rainbow of radio waves or gamma rays? So I guess, if I'm trying to interpret the question, you can imagine we see a rainbow of visible light broken up into the colors. could you get a rainbow of radio waves, or could you get a rainbow of X-rays, or could you get a rainbow of gamma radiation?
Absolutely, it's just refracting light of different wavelengths at a slightly different angle, and that's going to happen no matter where you're at. So yeah, if you had a gosh, I guess you could, if you had something making a rainbow effect, you could see it with a radio spectrometer that was splitting it up into different colors, radio wavelengths, or if you had a broadband system that would put it all into one data chunk, absolutely, you can get a rainbow effect.
That's why we have actually these the dome here, because we were talking about earlier this radar that they were doing of the moon with that big line feed antenna that's almost 200 feet long. If you've seen GoldenEye, it's the one 006 is hanging off the bottom of when Bond kicks them off. So they use that, but line feeds are really good at one frequency. Antennas really good at one frequency. So the reason they built the dome was that they could actually focus a wider band of radio waves to a point. So the instruments that are up in the dome here can actually look at a very wide set of frequencies in the range of gigahertz, multiple megahertz. So that's very cool. At radio, you have instruments that could see this, and yeah, you can get a variety. You can get a range of radio frequencies emitted from something, and if there was something that would diffract out radio waves like a raindrop does for light, you could totally observe it.
Neat.
Well, something similar to that would be Whistler, where you have different wavelengths, within the atmosphere traveling at different speeds, and so it separates out the different wavelengths of radio waves. And so if you pick these up, you can hear lightning strikes, for example, on the other side of the planet. And by the time they come through the atmosphere around the Earth, they're all spread out in frequency, and so you get this thing that sounds. That's why they call them whistlers.
That's the change in frequency, wavelength, color is
right, because the shorter wavelengths, the faster frequencies, they go faster than the longer ones. And we found them on Jupiter. We found them on Saturn. They happen when you have kind of electromagnetic waves that are trapped within a boundary.
Awesome.
I guess you can also kind of hear dispersion too. If you are on like a bridge that has cables, you can put your ear up to the cable and knock on it, and you'll hear sort of like pew pew pew, which is the mechanical sound waves dispersing into that cable. So that's sort of a wide range of frequencies that get changed.
Fun fact: the recording of those were used for the original laser beams for Star Wars.
No way!
Yep.
Dude.
They actually just recorded it next to a cable and tapped on them.
That's awesome.
That's awesome. Okay, cool.
I just pulled up a quick thing on the solar sibling, since somebody had asked about that earlier. The star that was the solar sibling, HD 162826, was the way that they have to look for these is they have to look at many, many stars that have a particular motion around the galaxy. So it's going to be in a similar orbit around the galaxy as the sun. And then take the fingerprint, the spectrum of all of these stars, and look at the fine details of the elements that they're made of. And so for this star in particular, it has the right velocity going around the galaxy to match up with the sun, and it has the right spectral fingerprint. So particularly they looked at the abundances of barium and yttrium, which are not things you usually talk about being in stars, but teeny tiny amount in the atmosphere was used to match it up to the solar spectrum to show that this is most likely from the same nebula that the sun was born in. So that's that. There's that story.
Barium.
I know. I think that's so cool because I mean it's a ridiculously hard project because you have to survey all of these stars, and they've been looking for this for a long time.
I want to make an M joke here. Barium, but he's not dead yet. Anyway. I broke Nicole.
Won't be the first time.
Awesome.
Okay, cool. Well, let's wrap things up. So before we go, though, let's let people know where and how they can find out more. Sondy.
Hi, I'm Sondy. I'm at Sondy on Twitter. I've been posting tons of Arecibo photos lately because apparently people really like those. So you should request some photos, and I'll probably put a blog post up on the Planetary Society website soon with photos.
Awesome. Brian Koberlein, where do we find out more?
I'm on Twitter at Brian Koberlein, and on my website, briankoberlein.com, and you can find me on Google+.
Sweet. Nicole Gugliucci.
I'm Noisy Astronomer on all the places, and I work over at CosmoQuest. So come over to cosmoquest.org and do citizen science with us. I have been looking at our citizen science numbers, and we got a big spike when we had a big news announcement about our published paper. That's starting to die down, so please do send your friends, send yourself over to the website and mark some creators in your spare time, during commercials, whatever. We're looking for more citizen scientists.
Well, and we've rolled out the new Mars mappers, so you can now find creators on
not
Mars.
Yet, not yet.
Not yet? All right.
We have announced it.
We haven't rolled it
announced that
out.
we will be building Mars
Right.
mappers. It's going to use the same software tools as the other projects, so if you're familiar with those
It'll
tools,
look pretty similar.
you'll go right in, and that'll make the development time much shorter.
And then also, we've still got some time for the Hangout-a-thon donations.
Yes.
So let's go to cosmoquest.org/hangout-a-thon, and you can still donate. And we're hoping to hit that. I don't know where we're at right now.
I don't know. It kind of petered off, man. You all make me sad.
You get to
We got a
support
few more
classes
donations.
like the one I'm teaching next week.
Yes, well, hang on. We got a few more
Donate to
donations
CosmoQuest.
last night as the contest for the big old chunk of meteorite from Planetary Resources. So that'll be announced soon. If you won dragon eggs from us, they're getting shipped out this weekend, I promise. But all those little thank you gifts are going out. So we're at 27,271 and 0 cents. So the 0 cents people are winning again. Yeah, Cosmo Academy. Go ahead, Sondy.
Yeah, there's a Cosmo Academy. There are classes on Cosmo Academy. I'm teaching one next week on asteroids. I'm sorry, it's full. I may do an encore in July or early August, depending on if there is demand. And you can learn all sorts of things about astronomical image processing, various objects in the solar system, or galaxies, or all sorts of stuff. So definitely check out the CosmoQuest classes. They're always looking for more people to take new faces to be in the classroom. So definitely check that out.
Yeah, that is like one of the coolest things that we do through CosmoQuest is that we allow regular folks, not even like master's degree folks, but regular folks with no formal education at all to come and join and take a class from a researcher in a topic of specialization that maybe you wouldn't even take even if you were getting your master's degree or such in astronomy, that you're going to sit down and learn for week after week just on astrobiology or just on asteroids or just on various aspects in cosmology. It's a really great service. So, and relatively inexpensive. Learn from Sondy about asteroids or the amount you might spend on some community class. So it's great.
And I know Emily Lakdawala taught one on, I think, astronomical image processing, so how to make pretty images from publicly available data from spacecraft. So that's pretty cool.
Yep.
The other class that's open at the moment is Black Holes from Dr. Matthew Francis. He's got 2 sessions open. So if you are in Europe, we have a time frame that's not totally bad for you. It's like evening in Europe, so check that out. That's the current offering, and I know he's working hard on lining up. I just sent a whole bunch of new potential instructors his way from my contact list, so hopefully there'll be some new ones coming soon.
Bert Walter says, please don't cancel the VSP. We try not to. We are ready to go every week, and then it just depends on the weather, and it just depends on the astronomers. So it's trying to talk about herding cats, trying to get a whole bunch of astronomers all together to broadcast the night sky live is pretty rough. So we apologize that it happens, and
you guys have had a rough spring.
If you could get, we're almost spring's been tough, and then once we get the backside of spring and into summer, then it gets a lot better.
Cloudy.
Very late. Yeah. Okay, cool. Well, once again, I am Fraser Cain, publisher of Universe Today, and go check out Universe Today or F Cain on Twitter or Universe Today on YouTube.
It's so weird when I get a tweet from you. It's like, oh my God, Fraser's on Twitter again.
I should tweet that right now.
You ignored us
that.
for so long.
All right. Cool. Yeah. Thanks everyone for watching. The next thing is going to be the Virtual Star Party, we hope. And if not, Astronomy Cast on Monday. So we'll see you all next week.
Bye.
Bye.